I'm going to start with a review of power of a point and the radical axis theorem. If you want to skip this, look in the video description for a bookmark to the solution. We define the power of a point, P, with respect to a circle O, as the square of the distance from P to the center of the circle minus the square of the radius. We define a radical axis of two circles to be the set of points that have equal power to those two circles. Let's say we have two circles, circles R and S, and let's place them on the x-axis so that the centers of our two circles are on the x-axis. So it looks something like this. Let's say the center of circle R has x-coordinate A and the center of circle S has x-coordinate B. And let's have the radius of our circle R be lowercase r and the radius of our circle S be lowercase s. We're looking for the set of points P that have equal powers to circle R and to circle S. By the distance formula, we have the square of the distance from P to R is equal to x minus a squared plus y squared. And the square of the distance from P to S is x minus b squared plus y squared. We want the power of P to these two circles to be equal. So PR squared minus R squared is equal to PS squared minus S squared. And substituting, we'll expand the squares and combine like terms and solve for x. Since our y terms disappeared, we have x is equal to a constant, which gives us a vertical line. Let's let A and B be the intersecting points of our two circles R and S. Since A is on circle R, we have the square of the distance from A to R is equal to the square of the radius. So the power of A with respect to circle R is 0. Similarly, since A is on circle S, we have AS squared is equal to S squared. So the power of A with respect to circle S is 0. These are the same powers. So point A is also on this vertical line. A similar argument can be made for point B, which is also on both circles R and S. So line AB is the radical axis. AB is also perpendicular to the segment connecting the centers of the two circles. Let's return to the problem. Let's make these our three circles, omega 1, omega 2, and omega that's tangent to these two other circles. Let's let the centers be O1, O2, and O. Let's start by connecting the three centers. By the radical axis, we have that AB is perpendicular to O1, O2. Let's let this intersecting point be S. We note that the distance from O1 to O is R1 plus R, and the distance from O2 to O is R2 plus R. Let's draw a perpendicular from O to the opposite side of the triangle, and we'll call this point T. If I draw a perpendicular from O to line PQ, and we call this point U, then we have that OU is the same distance as ST. Taking a closer look at circle omega, we have arc PQ is 120 degrees. So when we draw OU, we create a 60-degree angle here at O. So that means by the 30, 60, 90 triangle that the distance OU is half of the radius R over 2. Since S is on AB, which is the radical axis of our two circles, the powers of S to our two circles, omega 1 and omega 2, are equal. So we have SO1 squared minus R1 squared is equal to SO2 squared minus R2 squared. Take a look at the right triangle on the left, triangle OTO1. By the Pythagorean theorem, we have R1 plus R squared is equal to O1t squared plus OT squared. Similarly, for the right triangle on the right, triangle OTO2, we have R2 plus R squared is equal to O2t squared plus OT squared. Solving both of these equations for OT squared and setting them equal to each other. Expanding and rearranging terms. Now we note that the distance from O1 to T is the distance from O1 to S plus ST, and the distance from O2 to T is the distance from O2 to S minus ST. So we'll make that substitution over here. Now we're going to expand everything on the right-hand side, and we'll rearrange some terms. Now we note that O1S plus O2S is equal to the distance from the two centers of our circle, which is what we're trying to find in our problem. And the distance from S to T, we found that already. That's half the radius of our third circle. Then we note that this point S is on the radical axis of our two circles. So the power of S with respect to omega 1 and omega 2 are equal to each other. So we have the square of O1S minus R1 squared is equal to the square of O2S minus R2 squared. Solving for the squares of the distances from S to the centers of omega 1 and omega 2, we get this relationship, which we can also substitute over here. Let's rewrite the full equation. Now we can combine some like terms and solve for the distance. So we have the distance from the two centers is equal to 2 times the difference of the radii. These radii are given in the problem statement, so our answer is 672.